Hey folks, Ms. Gosling here. In this video, you're going to learn about conservation rules and Feynman diagrams. And by the end of the video, you'll be able to use the conservation rules for subatomic interactions and Feynman diagrams to determine the feasibility and structure of particle interactions. So you'll basically be able to determine whether a particle interaction can happen, and if so, what it looks like. So we're going to start with the conservation rules. And the first couple you guys are very used to. So first of all, mass energy total need to be conserved. So you've learned conservation of mass in chemistry, you learned conservation of energy last year. Now we're going to talk about how, now we know that mass and energy are kind of two sides of the same coin. So as a whole, our mass and energy together need to be conserved. Mass can turn into energy, energy can turn into mass, but the total mass energy thing needs to be the same. Momentum is going to be conserved, and charge will also be conserved. And you guys are used to that happening. The two things that are new are the fact that our baryon number and our lepton number also need to be conserved. So all quarks have a baryon number of positive 1/3, and all antiquarks have a baryon number of negative 1/3. So if we start with a baryon number, if we start with 3 quarks, we're not going to be able to end up with 3 antiquarks because that violates our conservation of baryon number. Similarly, lepton number also has to be conserved. All of our leptons, that's our electron, muon, and tau, are going to have a lepton number of positive 1, and our antileptons will have a lepton number of negative 1. And just to note, that includes all of our neutrinos as well as our particles themselves. Now, we also do need to talk a little bit about something called strangeness. Now, strangeness only is relevant for the strange quark and the anti-strange quark. Strange quark has a strangeness of -1, and its antiquark has a strangeness of +1. All other particles have a strangeness of 0, and so if there's no strange particle involved in our interaction, you don't need to worry about strangeness at all. Now, strangeness is strange in that it's only conserved sometimes. So if there is a weak interaction, we're not going to conserve strangeness. So if we're interacting through the weak nuclear force, we don't need to worry about whether strangeness is conserved. However, if we're looking at the strong nuclear force, we do need to conserve strangeness. So again, strangeness is conserved in the strong force. And I like to remember that as strange, strong. So our strong force conserves our strangeness. And they have that alliteration, and for me that helps. You may want to come up with a different mnemonic for yourself. Now, this brings us to Feynman diagrams. Feynman diagrams are so cool. So they are graphical visualizations of the interactions between particles. We also sometimes call them space-time diagrams because they show position on the x-axis and time on the y-axis. Now, there are a couple of key things to know about our Feynman diagrams. So, first of all, straight lines are going to represent particles. So this is an example of something representing a particle. So that is any of any of our quarks, any of our mesons, baryons, that is any hadron, and then also any of our leptons and our neutrinos. A wavy line represents an exchange particle. So these are our gauge bosons, our gluon, our photon, and our W and Z bosons. And we represent those by a wavy line to show that they are exchange particles versus our kind of more permanent particles that are always there. At every single, so what we'll see in these Feynman diagrams is we'll see vertices, for example, where two particles interact with one another, and they create a virtual particle, an exchange boson. So when that happens, we need to make sure that at each of our vertices, our charge, all of our conservation laws apply. So that is where we're going to be checking our conservation laws. Now, there are a few key Feynman diagrams that you really need to be able to do. So we're going to start with the Feynman diagram for the electromagnetic force. So let's say we start with two lovely electrons. So we have electron number 1 and electron number 2. Now, these electrons are starting out traveling towards each other. But then, and remember, these are our electrons that are existing at the same point in time, since they're at the same place on the y-axis. Now, our electrons, again, they start out moving towards each other in position as time goes on, but then they experience the electromagnetic interaction. So that means that we have to add the curvy line representing our photon, since that's our gauge boson for the electromagnetic interaction. And when they experience the electromagnetic interaction, because they have the same charge, they're going to go ahead and move away from each other. So they're going to bounce away from each other in space. We could do the same thing, replacing our electrons with protons. We could also look at what would happen if we had an electron and a proton interacting with one another. So again, electromagnetic force, particles come towards each other, virtual photon, they either move away from each other or continue to move towards each other, depending on whether their charges match or not. So from this, you should have been able to see what the process is for drawing a Feynman diagram. So first, we need to figure out which particles are interacting. Then, we need to figure out with which force are they interacting. So they're going to be interacting with the electromagnetic force, the strong force, or the weak force. And then finally, we need to know what is the force mediator. So is it a graviton? Is it a gluon? Is it a photon? Is it something else? We need to figure out if something is generated, is that final particle generated stable, or is it going to decay into something? So that's a lot of things. In our first Feynman diagram, we figured out, okay, so we have two electrons, that was given, and the electrons are interacting. Because they're both electrons, we know they're going to interact with the electromagnetic force, which is a force. So we have, again, two electrons. We're gonna interact via the electromagnetic force. The force mediator is going to be our virtual photon. And we don't need to worry about any new particles that are produced, since it is going to be just our two electrons continuing to interact with one another. So now let's look at the strong interaction. So again, we're going to start by drawing our position and time axes. Now, the strong force interacts between quarks, and therefore it interacts between nucleons, so anything that hangs out in our nucleus. And the most common exchange particle that we're going to see actually existing here is going to be for our pion. So we have a positively charged pion, a negatively charged pion, and a neutral pion. And guys, this is your reminder that often the strong force is going to be carried by mesons rather than seeing gluons themselves. Now, one thing here that I do want to mention, if you are given a force interaction, you should also be, specifically the strong force interaction, you should be told which pion is used. So you're not going to be asked to guess whether it's a positive, negative, or neutral pion, or whether it's a different particle, a different meson altogether. So if we have a proton interacting with a neutron, our proton and neutron are going to start out, again, traveling towards each other. And what will generate, and they'll interact via a neutral pion. And again, you don't need to have this memorized, just it'll be given in problems. Now, when they interact via a neutral pion, what we'll see is that they will just continue to move on, like so. So again, we have our proton and neutron interacting via the strong force. We know that it is probably going to be occurring via the strong force because the strong force mediates interactions between particles in the nucleus. So between protons, neutrons, protons, and neutrons. So that brings us then to the weak nuclear force. So the weak force is responsible for radioactive decay via beta emission. So beta positive or beta negative. So let's look at negative beta decay. So we have, again, our position and our time axis. And let's look at, for example, some negative beta decay, in which case, in our nucleus, we have a neutron that's going to turn into a proton. Now, we know that the exchange particles for this are the W and Z particles. And again, you should be told whether it's mediated by a W or a Z particle. In this case, it's going to be mediated by a W negative particle. When this happens, what we're going to generate is an electron and an electron antineutrino, which I am totally miswriting as just a positron. So here we go, our electron antineutrino. And we know this because this is how we can make sure that we are conserving our baryon number, our lepton number, and our momentum as well. So you'll notice our initial baryon number is 1, since we have one baryon, the neutron. And our final baryon number is also 1. Our initial lepton number here is 0, right? We don't have any leptons. So we have to have one lepton and one anti-lepton to ensure that lepton number is conserved here. Okay, now we're going to go ahead and look at pair production in and of itself. So again, we're going to start with our Feynman diagram by drawing our position and time axes. Now, in pair production, what we're going to do is we're going to start with a photon that's going to decay into an electron-positron pair. So that means at the beginning of time, we have a photon. And from that photon, we're going to get an electron and a positron. Now, one thing you'll notice, guys, for the electron, I drew my arrow going upwards in time, so pointing forward in time. For my positron, here, I drew my arrow going backwards in time. And that's actually another key thing that you should be aware of with Feynman diagrams. Antiparticles are represented by arrows going back in time. So the particle is not moving back in time, but that's how we show that it's an anti-electron, i.e. a positron, instead of a regular electron. So just a heads up there, that's something to be aware of when you're drawing these Feynman diagrams. Okay, so now let's talk annihilation. So again, we're going to start with the same position and time axes that we've had this for all of our Feynman diagrams. We have our position, which I'm going to just represent with S like we're used to doing, and time. So for annihilation, we know that annihilation is when a particle, so for example, an electron, and its antiparticle, so for example, a positron, meet up and turn into a photon. So that's exactly what we're going to draw. So starting at the beginning of time, we have our electron, we have our positron, and they're going to turn into a photon. Now, just so you know, that photon can then decay into other particles if it wants to. So this could result, for example, in pair production if we wanted it to. We're not going to worry about that now, however. And again, I do want to point out my electron and anti-electron, which are represented here as E positive and E negative. I could also represent them with what you're a little more used to, E and anti-E. And you'll notice my electron is pointed forward in time, and my anti-electron again is pointed back in time, just to represent that it's an antiparticle, not a particle-particle. Okay, so let's talk takeaways. First of all, the usual suspects are conserved in particle reactions, as are lepton and baryon number. Now, of course, when I say usual suspects, I mean mass, momentum, energy. Well, actually, okay, let's be more accurate, right? Not mass and energy separately, but mass and energy together, momentum, and charge. And then also our lepton and baryon number are going to be conserved as well. So if we start out with a lepton and an anti-lepton, we're going to end up with a total lepton number of 0. We're going to have to end up with a total lepton number of zero as well. So for example, an electron and a positron can't come together to create 2 electrons. So that's our first takeaway. Second takeaway, strangeness is only conserved in strong interactions. Strangeness is strange. This one is a little weird. Just gonna have to get used to realizing that that's not maybe one of the conservation rules you want to worry about as much. And then finally, Feynman diagrams are a useful tool for describing particle interactions. Perhaps a better word here might actually be depicting particle interactions, since they are kind of a drawn version, a graphical version of what a particle interaction equation might tell you. So there you have it, folks. Now it is your turn. Go ahead and try drawing some Feynman diagrams of your own. Best of luck and happy solving.